All right, so double integrals and volume. So we mentioned this a little bit last time, what it would represent if we had some kind of function inside our iterated integral. So that's really what we're going to talk about today. So what we want to do is find the volume of volume below a surface that's bounded by some region in the xy plane. So let me draw a picture here. This will be our setup. So we have some region in the xy plane. So this is R, and we have some surface up here. And we're going to say the surface is z equals f of xy. And we have a region in the xy plane here. So what we're going to do is divide this region into little rectangles. So at point x sub I, like so, and y sub I, like so, we're going to draw a little rectangle. And this x sub I should be at the center of that. And so one side of the rectangle, the area of that rectangle, we're going to call that delta y sub I, and the length of this side, delta x sub I. And we're going to approximate the volume of these little prisms. Make that a little more curved. So we have a little prism here. And what we're going to do is add the volumes of all of those prisms together. We're going to approximate. So we're going to approximate the volume of the solid, bounded by R, under z equals f of xy, by summing the volume of these prisms. And the area of the base of this prism is delta x sub I, delta y sub I, and the height is f of x sub I, y sub I. So the volume of one prism, v sub I, is f of x sub I, y sub I, times, I'll say delta a sub I, where delta a sub I equals delta x sub I, delta y sub I. And the total volume is approximately, it's going to be the sum, I equals 1 to n, of all of these volumes of these rectangles. And n is the number of prisms that we divided into. So I'm going to say that's approximately. And what we're going to do is take the limit as I approaches, or as n approaches infinity. So we're going to keep subdividing this into smaller and smaller little pieces in our region. Add up all those little volumes. We could also say this is the same as saying delta x sub I, comma, delta y sub I approaches 0, which is the same as saying delta a sub I approaches 0. And I'm being a little loose with the terminology here, because really what we do is we let the length, in order to make it work out correctly mathematically, we let the length of the longest diagonal of these rectangles approach 0. So that's what we let approach 0. But all these things mean essentially the same thing. We're going to take the limit as the number of our rectangles approach infinity, and we're going to use this as our definition of a double integral. So I'm going to switch pages here. So we're going to, that limit, the limit as n approaches infinity, this sum is going to be our definition of a double integral. That's how we're going to find the volume. So define the double integral and a double integral, the way we're going to write that is double integral over R. R is our region, f of xy dA. That is a double integral. And that is going to equal the limit, and I'm going to write it as delta A approaches 0, sum I equals 1 to n of f of x sub I, y sub I, delta A. Nope, this is just kind of down here below the two integrals. And this is our definition where this limit exists. And R is a closed bounded region in the xy plane. And z equals f of xy is a nice function. So it's continuous, doesn't do anything not friendly in that region. And we're also saying that because we're interpreting this as a volume, z is greater than or equal to 0 in R. So z is positive. So that's how we're going to define a double integral, is that limit. The properties of double integrals are very similar to properties of single integrals. You can add two together. You can multiply by a constant. You can subtract two double integrals. You can take the big volume minus the little volume, all those kinds of things. So I'm not going to list all the properties. They're what we would expect. The properties are listed in your book on page 976. They mirror the properties of single integrals. All right, well, this is similar to when we talked about the directional derivative. When we define the directional derivative as a limit, we need to know how to evaluate these things. How do we evaluate this? We don't want to have to take this limit, but thanks to a nice Italian mathematician by the name of Fubini, Fubini's theorem tells us that we evaluate double integrals as iterated integrals. So as long as all of those conditions are met, our function's nice, R is a closed bounded region in the xy plane, we can evaluate these things on as iterated integrals. So what we're saying is that for a vertically simple region, a less than or equal to x less than or equal to b, and g1 of x less than or equal to y less than or equal to g2 of x, the double integral over our region of f of x, y dA is the integral from from a to b, a to b, integral from g1 of x to g2 of x, f of x, y dy dx. So this is for a vertically simple region. And if we have a horizontally simple region, c less than or equal to y less than or equal to d, and h1 of y less than or equal to x less than or equal to h2 of y, then our double integral over our region of f of x, y dA is going to equal the integral from c to d, integral from h1 of x to h2 of x, f of x, y dx dy. So basically we're just putting in a function into our iterated integral. And for now we're going to interpret that as a volume below a surface bounded by our region R in the xy plane. We will use double integrals to do other things other than find volume as we move forward. But for now, that the volume interpretation gives us a way to think about double integrals. All right, so I just want to go through some examples. Really, what we're doing here is setting up iterated integrals. Most of what we do in chapter 14 is just various ways of setting up iterated integrals. We're going to interpret this double integral as various things, and we need to set those up. And setting them up involves looking at our regions and where things are intersecting, and translating that into our limits of integration. All right, we good? Okay. So here we have double integral over our region R, 1 plus x squared dA. And we want to set up for both orders. And R is the region bounded by y equals 0, y equals square root of x, and x equals 4. Now I recommend always making a little sketch of your region to help you set this up. So here's y equals square root of x. Y equals 0. And here is x equals 4. So this is my region. All right, so let's set this up first for vertical rectangles. So for vertical rectangles, y is going to go from 0 square root of x. X is going to go from 0 to 4, and we get y 1 plus x squared dy dx. If we set up for horizontal rectangles, we're going to go from x equals, we're going this way, x equals y squared to 4. And y is going to go from 0 to 2. Dx, dy. Which one of these is going to be easier? The first one's going to be definitely going to be easier, right? Because I get, when I integrate this with respect to y, I get a y squared over 2, going from 0 to x. Y squared, square root of x squared is just going to be x, and it turns into a nice u sub. If I do this, now you have an inverse tangent first, and you have to evaluate that on y squared to 4. That one would be kind of ugly. So I would choose to do the first one. I'm going to say easy, difficult. Or I would say less easy. How about that? All right, questions there? All right, sometimes instead of a verbal description of a region, you're going to be given a picture of the region. So let's look at one of those. So there is our surface, and our surface is going to be x plus y plus z equals 2. And remember, we want to integrate z equals f of xy. So I would rewrite this as z equals 2 minus x minus y. And this is our region in the xy plane. So let's draw a little picture of the region in the xy plane. Not to scale. Yeah, a little lopsided. And what's the equation of this line in the xy plane? Z equals 0. X plus y equals 2. All right, so let's set up our integrals. Double integral of f of xy dA equals, let's do our vertical rectangles first. Y goes from 0 to 2 minus x of 2 minus x minus y, and x goes from 0 to 2, dy dx. And that's going to be the same as, if I do horizontal rectangles, x is going to go from 0 to 2 minus y, 0 to 2, 2 minus x minus y, dx dy. Either one of these is going to be relatively easy. And again, I just want to point out on these last two examples, we're not just, to switch the order of integration, we don't just switch the things on the bits on the integrals and change the order. We don't change the x to y, x to y's, and just change the order. Doesn't always work that way. All right, questions there? Okay, let's look at another one. This one is, the region is a little trickier. This is a nice solid. And this is z equals 4 minus y squared. Y equals x. And this is y equals 2. And this is z equals 4. Z equals 4, there we go. So our region in the xy plane is this thing. So we need to be a little more careful with where our region is. There's y equals x. Here's y equals 2. So our region is here. And this would be x equals 2. So our integral for the volume, for vertical rectangles, x is going to go from, or sorry, y is going to go from x to 2. X is going to go from 0 to 2, and we have 4 minus y squared dy dx. For our vertical rectangles, and it's going to be the same as if we do horizontal rectangles. Y is going to go from 0 to x. Sorry, x is going to go from 0 to y. And y is going to go from 0 to 2. And either one of these is going to be easy to do. All right, questions? All right, I have a question for you. So R is a county in the U.S. F of xy is the total snowfall. At some point in R. First question, what does this represent? What would that be?
The amount of snow in the region.
And by a total amount, we mean the volume. This would be the volume of snow. Volume of snow, total snowfall, maybe. How about this double integral of f of xy dA over the double integral over our region of dA?
The average snowfall per unit area.
Right, the double integral of dA, if my function is 1, isn't that just the area of the region? Yeah? So this is snowfall per area. So that would be the volume of snow per unit area. Would be what that would represent. And this is an important idea to remember. The double integral over a region of dA is just the area of the region. And sometimes when you're evaluating double integrals, that can be helpful and save you some work. All right, one last question. We want to find the volume under f of xy equals 4x, and our region is the xy plane, in the xy plane, bounded by 0, 0, 4, 0, 4, 4, 0, 4 in the xy plane without using calculus.
Oh, we have a square. So I bet we should find the area in that square. I think that'd probably be useful to do.
Well, let's draw a picture. Here is my region. And that's 4, 4. And this is x equals 4, y equals 4, and that's at 0, 0. What is the surface z equals 4x? A plane. Parallel to which axis? Right, z equals 4x is a plane. Parallel to the y-axis. So in the xz plane, what do we get? A line, right? So isn't this going to be my surface, the volume that I'm looking for?
So it's a wedge. It's a wedge.
Yeah. It's a wedge.
Well, I bet we could find the area of the rectangular prism.
And what is this height?
4.
16. Z equals 4x. Z equals 16. So how do we find the area of this, the volume of this thing without using calculus?
Base times height times that.
Base, right? Base times height. Area of the base times the height, and then we divide by 2. And what do we get? 128.
So if you have a region that's all bounded by straight lines, you could probably do that.
If you all bounded by straight lines, you could probably do that.
You could probably avoid
All right, questions? Okay.